Brad Nye, the science guy.
That's a lot of momentum. Hi, I'm scientist Brad Zup, here to talk to you in this episode about momentum. Now, consider the following. Picture a fast-moving object, like a bowling ball hurling towards a lot of pins. Or even a scientist on a bicycle. Or maybe even a fast-moving car. No matter what object you thought of, as long as it is moving and has mass, it has momentum. This is why momentum is often thought to be mass in motion. Now, the formula for momentum is derived from mass times velocity. Both of these factors are directly proportional to an object's amount of momentum. Momentum is also a vector quantity, meaning it has both direction and magnitude. The direction of momentum is solely based upon the direction of the velocity vector. Now, try this. Get a tennis ball and a basketball and place them on top of each other vertically. And drop them. Now, we notice that the tennis ball bounces way higher than the basketball. But why is this? Well, the basketball is larger and has more mass, giving it more kinetic energy. Then, when the two balls collide, the kinetic energy is transferred to this ball, giving it more momentum. Neat, huh? Another way we can think of how mass affects momentum is with this at-home experiment. All you will need is a ruler, a quarter, and a dime. To start, we will align the coins at opposite ends of the ruler. Next, we will fling the quarter at this end of the ruler and observe what happens. As we can see, the quarter has moved the dime. This is because the quarter's momentum moved through the ruler and affected the dime. Next, we'll be seeing what happens when we use the dime instead of the quarter. As we can see, it barely moved. This is because a quarter has more mass than a dime, giving the quarter more momentum. Another concept I'd like to talk to you about today is the law of conservation of momentum. This law states that the momentum before a collision must equal the same amount of momentum as after a collision. The best way to demonstrate this is with this Newton's Cradle I've created out of popsicle sticks, string, and marbles. The way Newton's Cradle works is that as one ball is lifted, it gains gravitational potential energy. As it is released, it is transformed into kinetic energy. As it strikes the other four balls here, the collision creates a force through these three here, resulting in this one to lift upward. Now, you may ask yourself, why does only one ball move forward instead of all four, or maybe three or two? This is because the law of conservation of momentum states that if this one ball is displaced, then this one here is the equivalent after the collision. I will now demonstrate what happens if we move two of the balls. As two balls are moved, the law of conservation of momentum states that two balls on the other side should also be displaced. We can see that our hypothesis was correct, and this demonstrates the law of conservation of momentum. Let's give it some momentum. Science! He's running. He has momentum. He's running. He's running. He has momentum. He shoots the ball. That has momentum. Oh, he missed. He got momentum. Look at that shot. He's got momentum.